Here we have page 392, number 34. Our borders given to us are the square root of x and y equals x. I also think they describe this as the upper boundary and this is the lower boundary. Our axis of revolution for most of the problems in the 30s is the y-axis. Let's go ahead and make a simple sketch. We know that the square root function looks roughly like this. The key aspect of y equals x is that it starts off below the square root function. So the region bounded represents this little kind of banana-like sliver between this point and this point. We're ready to start asking some questions. Is it dx or is it dy? Is it a circle or is it a washer? And also, what's the role of each function? When we answer those questions, we'll be able to do slice, approximate, integrate with relative ease. The first question, dx or dy, the answer is dy, because our axis of revolution is horizontal. The second question, circle or washer, is washer, because our axis, which is also x equals 0, is not a border or not a boundary. Y equals x, y equals square root of x are our two boundaries. Neither of those is the function x equals 0, or should I say the vertical line x equals 0. So we have a washer problem and we have a dy problem. If we have a dy problem, we should relabel these curves appropriately. Our straight line, we need to think of as x equals y versus y equals x. Our nonlinear function, we need to think of as x equals y squared versus y equals the square root of x. If this is our axis, then relative to our axis, this is clearly our function that's farther away. So we're going to give it the label of outer. And for the region, obviously they crisscross, but for this specific region for our area, oh, I'm sorry, I mislabeled those. For this specific region, the nonlinear function is clearly closer. The nonlinear function is the inner layer. And for this specific region, the linear function is farther away. So it'll help us determine our outer. It's farther from the axis. The nonlinear is closer to the axis. We have all of our key elements, so we are ready to slice. We know that the area as a function of the big radius and the little radius, a of r comma little r is pi big R squared minus little r squared. Our approximate step is rewriting our variables as functions of y. We want big R of y because this is a dy problem. Big R is always outer minus axis. In this case, our outer layer is the function x equal y, so y. And we always want to write the right-hand side. This is the dependent variable, this is the independent variable, so that's what we want to use y. Our axis is the function x equals 0, so 0 is the rule for our axis. Simplified, the function y is our big R. Little r of y is found by inner minus axis. According to our picture, x equals y squared is closer to the axis of revolution. So y squared minus 0, our axis, gives us y squared as a simplified form. Now that we know big R of y and little r of y, we can go back and rewrite our area formula as a function of the variable y. A of y is pi y squared minus y squared squared, which is simply pi y squared minus y to the fourth. Now that we have big A, we can integrate and write an expression that finds our volume. Pardon the interruption. Mr. Greer has been paged to the main office. I hope he's here. The volume is the integral from A to B of A of y dy. Our A values and B values are going to be part of the y-axis. It's pretty clear from our sketch that 0, 0 is the A value, but the B value we need to find by setting y equal to y squared and solving. If y equals y squared, we know that y squared minus y equals 0, which means that y times y minus 1 equals 0. So this is actually a factored form for this quadratic equation. Our two solutions are either y equals 0 from this term, or y equals 1 from the other term. 0 was the one that was obvious. 1 is this value right here. So the volume is the integral from 0 to 1 of A of y dy. It was perfectly okay in the homework to evaluate this with a calculator, but this expression is pretty simple, and we could do it with antiderivatives if we wanted to complete the entire problem by hand. So on the next screen, I'm going to rewrite the integral expression and work it out with antiderivatives. We know that volume is the integral from 0 to 1 of pi y squared minus y to the fourth. It's good to factor out pi from our integral expression. It's not required, but it does make the antiderivative easier, and it definitely makes plugging in g of b and g of a easier. The volume is equal to pi, and then the antiderivative of y squared is y cubed over 3. The antiderivative of y to the fourth is minus y to the fifth over 5. Our A and B values are 0 and 1. So our volume is pi times 1 cubed over 3 minus 1 to the fifth over 3 minus 0 cubed over 3 minus 0 to the fifth over 5. I have an error at this step. This should have been a 5 from the y to the fifth over 5. This term clearly is 0 as a total, and here we'll have 1/3 minus 1/5. Or in other words, 5/15 minus 3/15, giving us a final volume of roughly 2 pi over 15. This pi is from the multiplication, and then 5 minus 3 is the 2. 2/15 times pi. At this step, we should draw a picture of an airplane to represent our dreams to travel to a faraway land and start a life anew. I started to draw an airplane, but I think at this point I'm going to transition into a shark to represent that we are hungry for math. Our shark has teeth, and our shark likes to eat eggs. It's a weird shark. That was page 392, number 34.